Hello friends, welcome to New Lessons. Today we will discuss about transistor biasing and the stabilization process. So you are quite aware of bipolar junction transistors, FETs, diodes. The main part is to use them in biasing. So in this video we will learn what is biasing, how biasing can be done, what are the methods of biasing. So first of all we'll start with transistor biasing. What is meant by transistor biasing? The basic function of transistor is amplification. As you all know, the process of raising the strength of weak signal into a strong signal is known as faithful amplification. Now there are some points to be kept in mind for faithful amplification, that is, the emitter based junction should be forward bias, collector based junction should be reverse bias, and proper zero signal current, that is the collector current. Now after reading all these things, you may not be aware of what actually is happening. So previously I have given you a video on multism where you can simulate all such things. You can open multism, you can simulate all such diodes, BJTs, you can follow the diagrams and you can observe how these BJTs are used in amplification purposes. You can measure the current across the emitter, base, collector, and you can do a lot of things. The proper flow of zero signal collector current and the maintenance of proper collector current emitter voltage during the passage is known as transistor biasing. So now, why biasing? If the transistor is not biased properly, what would happen? It would work inefficiently and the efficiency will decrease and it will produce distortion or noise in the output signal. These transistors are used for amplification purposes, and in the output we will find the efficiency very less and distortion and noise. So how a transistor can be biased? It can be biased either with the help of a battery or a circuit with a transistor. There are some special circuits regarding this we will study later. The next method, that is using special circuits, is more efficient and frequently used. The circuit used for transistor biasing are called the biasing circuits. Now, biasing stability. Though proper biasing, a desired Q point of the transistor amplifier in the active region. Active region, you know where the transistor acts, means the linear region of the characteristics is obtained. It is desired that once selected, the operating point or the Q point should remain stable. The maintenance of the Q point is called stabilization. The selection of a proper Q point generally depends on the following factors: the amplitude of the signal to be handled by the amplifier and distortion level in the signal, the load to which amplifier is to work for a corresponding supply voltage. These are some important points for selecting a Q point. Now the operating point of the transistor shifts mainly with changes in the temperature. Now this Q point is a variable of, means you can say is dependent on temperature, voltage and some parameters. Those are known as transistor parameters, that are beta, ICO and VBE. These are all the functions of temperature. Suppose you are given this circuit. If you are not familiar with this type of circuit, I want you to study with multism. You progress. These are very simple symbols made in this diagram. You can easily construct in multism. You can observe the output voltages, what is the VCC, what is the VCE, using a multimeter across this. So the more you will practice about this, the more you will familiar about this, and it will be better for you. Now coming to the topic, the DC operating point or the Q point. For a transistor circuit to amplify, it must be properly biased to DC voltages. The DC operating point between the saturation and the cutoff is called the Q point. This point lies between the saturation and the cutoff region. The goal is to set the Q point such that It does not go into saturation or cutoff when AC signal is applied. Now you should keep in mind all these things. What is the cutoff region? You might be familiar with. Cutoff region is where the emitter base is reverse bias and the collector base is also reverse bias. Saturation region is emitter base with the collector base both are forward bias. But in this case, emitter base is forward bias but collector base is reverse bias. That is known as the active region. Now what are the requirements of biasing the network? Ensure proper zero signal collector current, ensuring VC not falling below 0.5 for germanium and 1 volt for silicon. It depends upon the component which you are using. Germanium and transistor are basically used for transistor purposes. Ensuring stabilization of operating point, zero signal IC and VC. Now thermal stability of operating point, that is the ICO. Stability factor is given as S. The stability factor S as the change of collector current with respect to the reverse saturation current, keeping beta and VBE constant. Previously we have known the three parameters, that is beta, ICO and VBE. In this case, stability factor, the change of collector current with respect to the reverse saturation current, keeping beta and VBE constant. So this can be better written as, the thermal stability is written as SICO dou IC by dou ICO, that is a small change in IC and ICO when VB and beta is constant. So this is thermal stability factor. This equation signifies that IC changes ICO times as fast as ICO. Means if you see dou IC is equals to ICO multiplied with dou ICO, that means this value, the numerator changes signifies that it changes this much times, means the stability factor time as fast as ICO when VB and beta are constant. Now differentiating the equation of collector current, you get like this. You know, the collector current can be written as IC equals to 1 plus beta ICO plus beta IV, and hence ICO is 1 plus beta in terms of the different parameter, that is beta transistor parameter. It may be note, you should remember that lower the value of ICO, better is the stability. Means this is a thermal stability factor, lower its value, lower it the stability, means it will be not so prominent with the changes. There will be very little changes with respect to the environment, or you can say temperature. Now there are several biasing circuits. We can use, like the fixed biasing, common emitter biasing. You can see there are four types: fixed bias circuit, fixed bias or emitter resistor, that is a common emitter biasing, collector to base bias circuit, common collector biasing, and the voltage divider biasing. So first of all we will start with the fixed biasing. This is the symbolic diagram, or you can say this is the general diagram for fixed biasing circuits. In this case there is no resistor across the emitter, there is a resistor across the base and the collector. This is RB, RC, the current flowing through this base is IB, and current flow through this arm is IC. Now thermal stability, as we have seen before, is given as dou IC by dou ICO when BV and beta is constant. So the general equation becomes 1 plus beta by 1 minus beta of dou IB by dou IC. Now by applying KVL rule in this circuit, we can get IB into RB, current flow through this IB into RB, plus VBE equals to VCC. Now this using KVL at this stage is very easy for you, I guess, because we have read it in the first DC circuits part. Now differentiating with respect to IC, we get In this case, the thermal stability factor is very large, indicating high instability. The value of these factors when increases, that means they are more prominent with the changes of temperature of the environment. Now what are the advantages and disadvantages of this fixed bias circuit? As you can see the circuit, this is very simple to design, you have seen. So the first advantage in this case is it is simple to shift the operating point anywhere in the active region by just changing the resistance of the base. It is a very small number of components are required, but it has many demerits also, that is the disadvantages. The collector current does not remain constant with variation in temperature, power supply, voltage. When the transistor is replaced with another one, a considerable amount of beta is changes. That is the transistor parameter. Beta, alpha changes with the change of transistor. For small signal of analysis of transistors, example with not power transistors, with relatively high values of beta between 100 and 200, this configuration will be prone to thermal runaway. When the value of beta increases, a lot of heat will produce, and this will make the breakdown of this circuit, that is a thermal runaway. To ensure absolute stability of the amplifier, a stability factor less than 25 is preferred. Stability factor, that is S of ICO, should be less than 25, and so small signal transistors have this large stability factors. So here are some merits and demerits of these biasing circuits, fixed bias. Now what is the use of this circuit? You have seen there are three drawbacks of this circuit. So due to these drawbacks, fixed bias is rarely used in linear circuits. Linear circuits means those circuits which you use transistor as a current source. In that case, they will suffer from thermal runaway. Instead, it is often used as a circuit where transistor is used as a switch. Better to use it as a switch. However, one application of fixed bias is to achieve crude automatic gain control in the transistor by feeding the base resistor from DC source and derive from the AC output at a later stage. So for the timing, you must remember this transistor acts as a switch and not as a linear circuit. Now the second part is the common emitter or the fixed bias with emitter resistor. In this case, the same thing happens, but there is a added resistor, that is RE, across this emitter. In case of fixed bias, there was no resistors across this, but now in this case we have a resistor across this, and similarly we will use you will use it putting KVL and all. The fixed bias circuit is modified by attaching an external resistor to the emitter. The resistor introduces negative feedback that stabilizes the Q point, and this has also some merits and demerits. The merit is the circuit has a tendency to stabilize the Q point against changes in temperature and beta value. This is a very important merit of this part, that is it can stabilize the Q point itself with the respect of change of temperature and beta value, that is the transistor parameter. Now it suffers from some demerits, like as the beta value is fixed for a given transistor, this relation can be satisfied either by keeping RE very large or making RB very low. If RE is very large, very high VCC is necessary. This increases the cost as well as precaution. If RB is low, separate low voltage supply should be used in the base circuit. In addition to that, RE causes the feedback, AC feedback, which reduces the voltage gain of the amplifier. The extra resistor used in case of emitter causes the AC feedback, which reduces the voltage gain of the amplifier. Now it has also some uses, like the feedback increases the input impedance of the amplifier when seen from the base, and it is the main advantage of it. Due to the above disadvantages, this type of biasing circuit is used only with careful considerations of the trade-offs of the involved. Means with some limited quantities of RE and RB we can use it. Now the next part is a common collector part, that is, in this case, this is the general diagram of the collector to base bias circuit. This configuration employs negative feedback to prevent thermal runaway. Negative feedback is given for the thermal runaway. You can see the feedback path, the circular path. The base resistance RF is connected to the collector instead of connecting to the DC source VCC. So any thermal runaway will introduce voltage drop across the RC resistor that will throttle the transistor base current. Now simply applying KVL, we can use VCC equals to IBIC plus into RC plus IB into RF plus VB, and again differentiating with respect to IC, we get the stability factor in this case is 1 plus beta by 1 plus beta into RC by RC plus RF, and this which is less than 1 plus beta means this shows that it has a better thermal stability. That means it is not so prone to changes of temperature and parameters. It has also some merits and demerits. The first merit is it stabilizes the Q point against variation of temperature in beta, that is the replacement of transistor is E. Demerits is as beta value is fixed and generally unknown for a given transistor, this relation can be satisfied either by keeping RC fairly large or making RF very low. That means the collector resistor should be very large and the base resistor should be very low to get a approximate fixed value of beta. Now there arises two cases. If RC is large, a high VCC is necessary, which increases the cost. Precaution should be necessary while handling. And if RF, that is the base, is low, the reverse bias of the collector region is small, which limits the range of the collector voltage. And if the base current is small, it will limit the range of the collector voltage and leaves the transistor in active mode only. So the resistors RF causes an AC feedback, reducing the voltage gain of the amplifier. This undesirable effect of the trade-off for greater Q point stability. This is quite undesirable, but as it has greater Q stability, it can be used. One of its uses, the feedback also decreases the input impedance of the amplifier as seen from the base side. Due to the gain reduction from feedback, this biasing is formed only from the trade-off stability is warranted. So keeping in mind the advantages, its disadvantages, which can be used in several purposes as we have seen before for the first two things. Now the one last is the voltage divider circuit, that is the potential divider bias circuit. It is the best one, I would say. It's the most commonly used arrangement for biasing as it provides good biasing stability. In this arrangement, the emitter resistance RE provides stabilizations. The resistors RE causes a voltage drop in the direction so as to reverse bias the emitter junction. Since the emitter base junction is to be forward biased, the base voltage is obtained from R1 and R2 network. The DC based circuit is independent of the transistor current gain. In case of amplifier, to avoid the loss of AC signal, a capacitor of large capacitance is connected across RE. The capacitor offers a very small reactance to the AC and it passes through the condenser. So these are the basic idea about using this potential divider circuit. To know more, you can draw it, you can simulate these diagrams, you can realize how the amplification happens, how the parameters changes. So this is the basic simple diagram of a voltage divider circuit. Whenever you see from the base side to the emitter side, we find RTH. We have to find RTH, which is equals to, means we have VCC going across R1 and now parallelly distributed to IB through the base and R2. So the Thevenin resistance we have to calculate across R1 and R2, which comes to be R1 R2 by R1 plus R2. That means they are both are in parallel. And similarly VTH, that is the voltage across R2, will be total voltage into R2 by R1 plus R2. This is a very easy, as you have learned in DC circuits about how to use the voltage divider rule, current divider rule, equivalent resistance. Now to find the stability of the circuit, we have to convert the circuit into Thevenin's equivalent circuit as we have seen, and after converting into Thevenin equivalent circuit, we have got the values. This RTH is equals to the parallel combination of R1 R2 and VTH equals to VCC into R2 by R1 plus R2. Now again applying KVL after converting it into the RTH, here you can find a loop. IB into RTH plus IC plus IB into RE plus VB gives the VTH. And differentiating with respect, again we get the stability factor as 1 plus beta by 1 plus beta into RE by RE plus RTH. This shows that the stability factor is inversely proportional to RE and it is less than 1 plus beta. That means whenever it is less than 1 plus beta, it signifies better thermal stability. Now these are some merits and demerits. The first merit is the operating point is almost independent of beta variation. This is the most important merit of this type of circuit. That is, even if you change the transistor, the parameter beta does not change so much. Means the operating point is almost independent of the beta variation, means frequently you can change the transistor. The operating point stabilizes against a shift in temperature. Now the demerit is, as beta value is fixed for a given transistor, this relation can be satisfied either by keeping Re fairly large or making the Thevenin resistance, that is the parallel combination of R1 and R2, very low. If Re is of large value, high VCC is necessary. This increases the cost and as precaution necessary for handling. And if R1 and R2 is low, either R1 is low, R2 is low, or both are low, a low R1 raises VB closer to VC, reducing the available swing in the collector voltage. That means a collector voltage which will get will be very low. A low R2 lowers the reducing the allowed collector current also. So lowering both resistors values draws more current from the power supply and lowers the input resistance of the input amplifier as seen from the base side. AC as well as DC feedback is caused by Re, which reduces the AC voltage gain of the amplifier. Now it has a use. The circuit stability and merits as above make it widely used for linear circuits. This is the most important thing. These are widely used for linear circuits. Now to sum up for our video, I want to add some points like the Q point is the best point for operation of a transistor for a given collector current. The purpose of biasing is to establish a stability factor or a Q point. The linear region of transistor is a region of operating with saturation and cutoff, that is the active region. And out of all the biasing circuits, potential divider circuit or the voltage divider circuit provides the highest stability to the operating point. Now before completing our video, I want to say this type of circuits are very used in our daily life. Even if you don't realize them, even if you don't see them with our own eyes, they are used. So you need to simulate them in multisim, you will get more idea. And one more thing is, you need to practice more numericals on this. Thank you.